Yadagiri, working as Assistant Professor in Triple Department in Marri Laxman Reddy Institute of Technology and Management. So today I am going to cover the topics, that is AC through pure inductor and AC through pure capacitor. So let us see the circuit here first. So we are applying AC supply to this inductor. So alternating voltage we are applying to the pure inductor. So then alternating voltage is flows into that inductor. So that is given by V equals to Vm sin omega t. So in previous lectures we have discussed the standard equations, that is voltage and current. So it is related as, so V is equals to Vm sin omega t less or minus phi, and I is equals to Im sin omega t less or minus phi. So these are the basic standard equations. So let us see the equation 1 and compare the basic standard equation of A and basic standard equation of B. So from this we can relate that the phase angle, that means the voltage starts at 0 degrees. That is, here the phi is 0. That means here the voltage starts at 0 degrees. Okay, so that is keep in mind here. So now let us find what is current flows into the circuit. So as you know that the current, the relation, the voltage across the inductor relation, that is V is equals to L into di by dt. So from this relation we can derive the current expression. So that is the current flows into the circuit. So let us see that we are applied sinusoidal voltage, that is V equals to Vm sin omega t to the inductor. Then what happened here? This voltage across the inductor is same as the supply voltage. So let us take that the V is nothing but Vm sin omega t, and L equals to, which equals to L into di by dt. So from this expression we can derive that so this take this dt to this side, and we can find the IDI. So that is Vm by L into sin omega t is the dt. So here we have to integrate on both sides. So integrate on both sides. So then what happened? We can get the current expression. So once we are integrating the both sides of this expression, then current I equals to Vm by L into integration of sin omega t into d omega t we are getting. So integration of sin, as you know, that is minus cos omega t, and omega t integration is by omega. So that is current I equals to Vm by omega L into minus cos omega t we are getting. So from this, if we can rewrite this expression in terms of sign, then we can see that is current I equals to Vm by omega L into sine of omega t minus pi by 2, or we can write that same expression, that is I equals to Im sine omega t minus pi by 2. So let us take this expression number 2. Now we have to compare this expression number 2 with the standard expression, that is expression number B here. So this is the B expression we have to compare here. So once we can compare here, then we can know that the phi is nothing but, that is minus phi by 2. That is phase angle phi is minus phi by 2, or it is nothing but minus 90 degrees. So that means here current is lags the voltage by an angle of 90 degrees. Okay. So here the maximum current is given as, that is Im is equals to Vm by omega L. So what is omega L? That is we will see now. So this is the voltage and current expression. So from the equations 1 and 2 we can observe that pure inductive circuit. So you can see here the current I lags the voltage at an angle of, that is 90 degrees. So here we can see it is voltage is started at 0 degrees. After 90 degrees the current will start here. So from this phasor relation and the waveforms we can observe here is that, so the voltage waveform you can see it is started at 0 degrees here. So the voltage it starts at 0 degrees and it attains the maximum value, and it attains the minimum and attains the 0 value at omega t equals to 5 radians. See what is after 90 degrees you can observe here. So after 90 degrees or pi by 2 radians, the current is starts. That means here from this waveforms we can say, from this phasor diagram we can say that the current I lags the voltage in pure inductive circuits. So in original case, actually there is some, if it is the inductor is not pure, so then the phase angle will be different. But in pure inductor, the current lags the voltage at an angle of 90 degrees. That means once once the voltage starts at 0 degrees, after 90 degrees the current will starts here. Okay. So how it is means, by the expression we see that expression 1 and 2 we have seen, and in the expression 1 we have seen that phase angle phi is 0, that means the voltage starts at 0 degrees, and from the second expression the current, that is phase angle phi is it is minus 90 degrees, so that means current is lags the voltage at an angle of 90 degrees. Now coming to the inductive reactance. So as you know that this is omega L, so that is so omega L is nothing but, so before going to discuss, so what is the inductive reactance? So inductive reactance is the opposition offered to the flow of alternating current. So it is like same like as it is equivalent to the resistance of the circuit. So it is nothing but it opposes the flow of electric current. It is one type of resistance in terms of DC circuits. So in case of AC circuits, the inductive reactance is the opposition offered to the flow of alternating current. So it is also one type of resistance. So it is called as inductive reactance. So the inductive reactance symbol is XL. Okay, so that is X suffix L. So it is given as omega L or 2 pi FL. So it is a frequency dependent. So inductive reactance is a frequency dependent. So XL is equals to omega L or omega 2 pi FL. So it is equivalent to the resistance in case of a DC circuits, and the units for the inductive reactance is ohms. The units for the inductive reactance is ohms. So coming to the power. So instantaneous power and average power. So first we will see the instantaneous power. So the instantaneous power we can define as the power P equals to the instantaneous power. All instantaneous quantities we can represent in the small letters. So that is P equals to V into I. So where V you already know. So from the expression 1, that is Vm sin omega t, and from expression 2, I is nothing but Im sin omega t minus pi by 2. So if you can do the product here, and then you will get that the P is equals to minus Vm Im sin omega t into cos omega t. So that is nothing but if you can take that sin omega t, multiply with the 2 and divide the 2, then you are getting as P equals to minus Vm Im by 2 into sin 2 omega t. So that means here you can see from the instantaneous power expression, so it is the fluctuating in nature. So that means we are getting as 2 times of the angular frequency. So 2 times of the angular frequency means over a complete period of cycle we are getting the two fluctuations we are getting here. So that means here the nature of the power, the instantaneous power is fluctuating in nature. The instantaneous power is fluctuating in nature in inductor. So based on that we will see that what is average power. So average power, so from the instantaneous power we can find the average power over a one complete cycle, that is as follows here. So over one complete cycle the average power is gives that P equals to 1 by 2 pi integral 0 to 2 pi. That means we have to cover the total cycle here. So what is for this total cycle 2 pi. So for this complete cycle, so that is pi to 2 pi. So for this complete cycle, then what is the average power? So that is the general expression we have seen here, 1 by 2 pi into integral 0 to 2 pi and the instantaneous power, the integration of the instantaneous power. So if we can integrate and so simplify this one, then finally we are getting as the power is 0. The power is 0 because it is in the fluctuating in nature. Then the average power is 0. That is over a period of time. So that is positive power and negative power we are getting. So positive power and negative power we are getting. So that is the average of this power will gives the total power is equals to 0. That means here average power in pure inductor is circuit is 0. Or in other words, power consumed by the pure inductance is 0. Power consumed by the pure inductance is 0. Okay. So that we'll see the waveforms here. So the voltage, current and power waveforms. So as you see here, the waveforms for pure inductive circuits. So the black color indicates here the it is voltage starts at 0 degrees. So the black one indicates the voltage. So that is V equals to Vm sin omega t. So that is V equals to Vm sin omega t. So it starts at 0 degrees, and the current starts at after 90 degrees, because what is the current expression? The current expression that is equals to Im sin omega t minus pi by 2. Minus pi by 2. So minus pi by 2 in the sense what here the current starts at after 90 degrees. As you see the phasor diagram also, you can see this is the voltage is the reference one, and the current starts at after 90 degrees. The current starts after 90 degrees. Okay, now we can see the power expression. So that is power is equals to the average power is equals to 1 by 2 pi integral of 0 to 2 pi minus Vm Im by 2 into sin 2 omega t. So from this expression we can see the power, the average power over a complete cycle you can see here, that is it is the starts at here. So that is the minus, it is a negative sign here because of just the power is started in the negative direction. So over a period of cycle we can, over half cycle we can see it completes the 2 cycles. That means here the power is fluctuating in nature. Okay, because 2 times the omega frequency is there, so 2 times the angular frequency. So that means over a period of cycle, over half period of cycle we are getting as the fluctuating power. So that means here if you can do the average of these two, that is positive, the negative and positive is 0 here over a half period of cycle, and you can see the negative during negative half cycle also the power is positive here and the power is negative here. So the average of this both the powers will be 0. So that's why the inductor will never consumes the power. So it will only it will generate. So property of the inductor is, so it will stores the energy only. It will stores the energy in the form of magnetic field. So it will never consumes the power here. So that is the conclusion for pure inductor circuits. So finally we will see that so the instantaneous power is positive, alternatively positive and negative here. So when power is positive, then what happens? Power is flows from source to inductor. That means here when P is positive, here power is positive. That means the power is flows from source to, the power is flows from source to inductor. Source to inductor. When the power is negative, then what happened here? So then the power is negative. The power is flows from inductive to the source. The power is flows from inductor to source, that is inductor to source. So that means here positive power is equals to the negative power, hence average power in the circuit is equals to 0. So just power just flows between the source and the inductor. The power is just flows between the source and the inductor. It will never consumes the power. So inductor does not consume the power. So this is the conclusion. Okay. So that means inductor will never consumes the power. Okay. Next we will relate this the voltage, current and power, voltage and current relations in the phasor algebra for pure inductive circuit. So we can see here in the phasor algebra we can take that as a V equals to V at an angle of 0 degrees. So it is expressed in polar form. So now it is converted into rectangular form, that is V plus J0. Okay. So here the current we can express as from the expression 2. So that is current I equals to I at an angle of minus 90 degrees, because current lags the voltage at an angle of 90 degrees. So we can convert this polar form into rectangular form. We are getting as 0 minus Ji. So if we can take the ratio, that is V by I ratio, then we are getting the XL. So that is XL is nothing but XL at an angle of 90 degrees. So finally we can express that V equals to I into JXL. So finally we can represent in the phasor algebra form, if we can represent the voltage and current and inductive reactance, that is V equals to I into XL. So that is nothing but it is the voltage drop across the inductor. So I into XL. Okay. So this is the phasor algebra relation for the pure inductive circuit. Next, coming to the second topic, that is AC through pure capacitor. So here also the circuit shown in figure here. So here we have to apply AC supply to the capacitor then what are the changes in the voltage, current and power relations that we are going to see, and what from that relations we have to conclude that what is the power, whether power is consumed or not. Okay, so as you know the property of the capacitor is a, it is a device which will stores the energy in the form of electrostatic field. Okay, so consider here the same case here, we are applying the AC supply and I can represent that as a V equals to Vm sin omega t. I am going to apply to the my capacitor, that is pure capacitor. Then current starts flows, then current flows to the capacitor, then we have to derive that current expression. So here also we can see that phase angle phi is 0 here, that is we have to compare this expression with the standard expression AA. Then we have the phase angle between the, that is phase angle is 0 by this expression we can say. So next coming to the current expression, if we can derive the current expression, first we have to find the what is the charge stored in the capacitor. So the charge stored in the capacitor, that is Q equals to C into V. So that is nothing but the C. So V is nothing but Vm sin omega t. So that we are going to apply here. So V into sin omega t. So then by this amount of charge stored in the capacitor, then we can find the current expression. The current E is nothing but the rate of change of charge. So that is current I equals to dq by dt. So that is I equals to dq by dt is the current flowing into the capacitor. So we can substitute this Q in the current expression, then we can say that current I equals to, so here the current I equals to d by dt. So what is the current Q charge expression, that is equals to C Vm sin omega t. So C is a constant here, so then we can take outside, so then we can get C, and if we can derive the derivative of sine, you can see that derivative of sine is equals to cos omega t into omega. So Vm is also the constant into omega. So that is the general current expression. We can say here the current I equals to C Vm omega into cos omega t. So I can convert this into my standard expression. So in terms of sine, that is equals to I into omega C Vm into sin omega t plus phi by 2. So from this expression, so from this expression I can convert that is into I equals to Im sin omega t plus pi by 2. I equals to Im sin omega t plus pi by 2. So from this expression we can say that the phase angle is plus pi by 2 or 90 degrees, plus pi by 2 or 90 degrees. That means here the current leads the voltage at an angle of 90 degrees. Okay, so where Im is nothing but the omega C into Vm. Okay, so what is Vm? What is Xc that we are going to see here now. So by this expression 1 and expression 2, we can see the waveforms also, waveforms and phasor diagram. So here we can see the voltage starts at an angle of 0 here, so that is it is taken as a reference, and after 90 degrees, that means here, that means already current is leads here. So how much of the current is leads here? So 90 degrees. So that means here so current leads the voltage. Here in inductor current lags the voltage, but in capacitor current leads the voltage at an angle of 90 degrees. This is only for pure cases, pure capacitor and pure inductor cases. Okay, so then what happened here, the current, whatever the current is there, that leads the voltage at an angle of 90 degrees. So from the phasor diagrams also you can see here, so this is the voltage starts at 0 degrees here, and current you can see here. So current is already started here, after you can see the, so current is leads here almost 90 degrees. Okay, so that means here current leads the voltage at an angle of 90, or we can say that if we can take the current as a reference, then voltage is lags the current by at an angle of 90 degrees. Okay, so here now we can see the what is the capacitive reactance. So capacitive reactance, first we will see the definition. It is the opposition offered to the flow of alternating current. It is the opposition offered to the flow of electric current, flow of an alternating current by a pure capacitor. So it is called capacitive reactance. So it is also similar to that resistance in your DC circuits. So resistance in your resistive circuits. So that means the capacitive reactance is also offers the opposition to the flow of an alternating current. It opposes the flow of electricity. Simply says that the capacitive reactance is also oppose the flow of electric current. So the capacitive reactance can be expressed as Xc. So that is equals to 1 by omega c. So I can write this as a 2 pi. Omega is nothing but angular frequency. We can write in terms of normal frequency, that is equals to 1 by 2 pi fc. So here the capacitive reactance is also depends upon the frequency here. Okay. So if the more the frequency, the capacitive reactance will be less. So if the less the frequency, then the capacitive reactance will be high. Okay. So here the units for the capacitive reactance is ohms, same like as the resistance. Okay, so that we have seen in the inductive reactance is also same units, that is ohms, and capacitive reactance is also same unit. So property will be same for the capacitive reactance and inductive reactance. Okay, it will oppose the flow of an alternating current. So now let us see the instantaneous power. So in the same case what we have seen in the inductor, so here also the instantaneous power is equals to, it's a product of voltage and current. So what is the expression for voltage? That is Vm sin omega t, and the current expression we have derived that is second equation, Im into sin omega t plus pi by 2. So if you can take this product, then finally we are getting as Vm Im by 2 into sin 2 omega t. So this is the instantaneous power we are getting here. Okay, so and from this expression we can say this, the angular frequency is 2 times the 2 times of the angular frequency. So that is, it is a fluctuating in nature. So that is, it is not a stable one. So 2 times of angular frequency means it is fluctuating in nature. So now the average power. So average power from this, from the instantaneous power, we can find the average power over a complete period of cycle. So that is, the power expression is given as, that is power P equals to 1 by 2 pi integral 0 to 2 pi Vm Im by 2 into sin 2 omega t into d omega t. So here, by after discussing, see here, the power, average power consumed by the capacitor is equals to 0. So that is, average power in a capacitor is 0, that is power consumed by pure capacitor is 0. So a capacitor is not consumes any power, it will stores energy in the form of magnetic field. So that is the energy stored by the capacitor, we can say that half into CV square. So this is only stores the energy. In the same way, the inductor, the inductor it also stores the energy. So the energy stored in the inductor is equals to half into Li square, half into Li square. So that means both the inductor and the capacitor will stores the energy, but it will never consumes the power. Okay, that is a conclusion from the pure capacitor.